So let me begin by thanking Shayan, Stefano, and in particular Nilima, Hilda, and Ram for organizing this meeting and carrying the torch for all of us for the nonlinear dynamics community. So I'm going to talk about something that's sort of ongoing work. So I'll essentially present the gist of where we are at. Something that I'm sort of mildly excited about, and I'll let you all be the judge if the excitement is not essentially warranted. Also, because of the younger audience, I will try, the first 2/3 of the talk will essentially be a little background into the context of that field, how best I can summarize that in a few minutes. So essentially, if you're just thinking of turbulence, and fully developed turbulence, this is the sort of definition that we'll be at. So I'm going to talk about flows which are at very high Reynolds number, hence turbulent, and they're in some sort of non-equilibrium state where you have a constant energy injection and which is sort of balanced on average by viscous dissipation. So the telltale signatures, and we'll come to these in slightly more detail, is the fact that these flows are, of course, chaotic, they're irreversible, they're intermittent, and they have multiple length and time scales. So where does one sort of start to think about it? So the basic framework to understand, and I emphasize the word understand, and you'll see why, is essentially to look at the Navier-Stokes equation, which governs these flows. So what I told you about in the earlier slide would really be solutions to this equation when the viscosity is very small with appropriate boundary conditions, which could be periodic, which makes sort of life simpler for us who sort of struggle to deal with real boundaries. And the essential sort of question, so this equation remains invariant under these scalings, and the essential question which sort of governs, and this will come up repeatedly in my talk, is what is this Holder exponent h? How do we fix this value? All right, and this sort of does not come about naturally from the equations themselves. So this sort of goes back, and as I said, the first 2/3 is really for the younger people in the audience, and I'm very happy to discuss this with you today, tomorrow, even whenever. Goes back in trying to understand how to fix H, goes back to the work 100 years ago, actually, to Louis Fry Richardson, who sort of gave us a model on how transfer of energies happen. And you'll see why this sort of rather simple model, and it's amusing that Richardson himself derived this from Jonathan Swift's parodies, is how energy gets transferred from large to small scales. And the picture that Richardson had was that if you have an energy injection at really large scales, then they get transferred to smaller and smaller scales till viscosity, which is somewhat like friction, sort of rubbing fluid passes against each other, and that energy tends to dissipate. So this idea was then taken up by Kolmogorov in 41, and that's the sort of standard sort of framework in which people like us like to work on. And sort of Kolmogorov used that idea to talk about, all right, so there is energy injection, there is dissipation, and on average, these happen at very different length scales. So what you have is the energy which is injected, then cascades, to use Richardson's words. So there's a constant energy flux, which then gets destroyed by viscosity. Hence, you have the relation, the mathcal P equal to pi, oh, sorry, this works, I guess, yeah, pi equal to epsilon. So the self-similar notion of this field, sort of, which was Kolmogorov's great breakthrough, was that if I start to worry about what happens to the correlators of this velocity difference, where r is within the scale where the flux is constant, then you can sort of go ahead and predict this sort of famous p/3 scaling exponent turbulence. But it turns out that this is, and this, you remember, I began with the idea of the Holder exponent. This sort of shows trivially that within this sort of mean field argument of Kolmogorov, the Holder exponent is 1/3. So the field is not really smooth. It's not Holder equal to 1, but it's 1/3. And this 1/3 is sort of a crucial number. So the Kolmogorov picture in a sentence would be that essentially turbulence is a non-intermittent process. So there is a constant flux of energy, and this flux of energy, as it cascades through length scales, eventually accumulates on three-dimensional structures which are small enough for viscosity to be relevant, and the dissipation is happening on these three-dimensional structures. So as we know, and this is no surprise, that when you actually go ahead and measure these exponents that Kolmogorov predicts to have the value of p by 3, you end up getting exponents which are certainly not p by 3. And this sort of goes by the sort of common name of turbulence being multiscaling. And this sort of settles the argument in some way that the Hölder in turbulence cannot really be 1/3. Again, this is known for a while. The question really becomes, is it greater than 1/3 or less than 1/3? And this has to do with sort of issues of weak solutions and dissipative solutions, etc. Again, something we can postpone for a later discussion. So the question then becomes, how do we go beyond Kolmogorov? So this Kolmogorov picture, how do we sort of try to work around it to actually figure out where this sense of multiscaling comes in? And this goes back to the ideas of the multifractal rationalization, which was introduced by Frisch and Parisi in the mid-90s, which essentially, you know, the physical picture essentially is the following. So you had the Richardson picture, which was space filling. So you had a big eddy of energy, and that eddy sort of breaks down into smaller and smaller segments, which are still space filling. What Parisi and Frisch argued was you can break that picture. Actually, it goes back to earlier studies of Nelson and Solem as well, is you can make this process not space filling. So locally, if there is an energy, bulk of energy, as the structure breaks, there could be structures which carry no energy or which are not active. And once you break this idea of space filling, you make things fractal, then you essentially depart. This is just for completeness, so don't bother reading about the three hypotheses which go into. Then you go from 1941 Kolmogorov to 1985, and the essential point is that Kolmogorov implied a single scaling exponent, the Hölder exponent h 1/3. The Frisch-Parisi model allowed for a range of Hölder exponents between an h min and an h max. The model itself does not tell you what h min or h max could be. It just allows you the freedom to choose a range of Hölder exponents, and what it in the end is the fact that we had seen the experimental data. So these are again the scaling exponents, that's Kolmogorov, and you know, taking the Frisch and Parisi model to its sort of logical conclusion allows you to have a better rationalization, not a theory, of this sort of nonlinear convex behavior of these scaling exponents, right? So this is, fantastic, and so it gives us a handle to actually tackle the turbulence question. So again, I'm still at the sort of introductory level, and this is not really for, you know, the experts and senior people, but let me sort of tell you how this works as simply as I can. So the way it works is, so the basic idea, and so these also go back to earlier studies, and this paper by Minerva and Srini, there were a bunch of papers at that time, but this in particular is sort of very easy to follow if you want to play around these models. So the idea is the following, that the energy dissipation field, which is embedded in 3 dimensions, we are talking about 3-dimensional turbulence, let's say data from a wind tunnel, it's sort of, the essential idea is that the dissipation field is now not going to be 3-dimensional structures, there's enough experimental evidence for that, but is going to be an interwoven fractal subsets, each with a different scaling exponent. This is a little hard to visualize. We'll come to the visualization in a bit. What one is arguing is that there could be different scaling exponents, and associated with each scaling exponent, so you take a little sort of width around a unique scaling exponent alpha, you associate a fractal dimension. So your dissipation is happening on different structures. Each of them correspond to a different scaling exponent, and hence a different Hausdorff dimension or any of your favorite dimensions that you want to worry about. And this, by the way, this alpha is easy to show, is exactly 3h, the standard Hilbert exponent that we are talking about. So now the question is to compute these exponents. So what one does essentially is, so this is a sort of trace of the dissipation field over space. So you have these sort of intermittent spikes. Kolmogorov would have told you that this is going to be a flat line. So what one does is we can actually break this sort of time or spatial series into little boxes of different sizes and then compute the total dissipation in each of these little boxes, right? So if things were monofractal, then the sum would be constant, and you would end up with alpha equal to 1, and you'd end up with a total energy which is just to be proportional to the spatial dimensions on which you construct these boxes, right? However, if things are intermittent or things are spiky, that's unlikely to happen because you will find boxes where there's nothing, or you will find boxes where there is a lot of stuff going on. All right, so that's the basic picture. And from here, you can construct a standard partition function. I mean, that may not be the most appropriate choice of words, but I'll go with partition function. And you can sort of raise this object to the power q, etc. And then you find a beautiful scaling with a generalized dimension q. Right? So qth power of these guys, and you end up with dq. So, and from there, with a bit of algebra, you can actually compute alpha, the same alpha that you have here, and you can actually compute the fractal dimension of the sets on which your dissipation is happening for a given alpha. So just to sort of, fix ideas, so if you're thinking of Kolmogorov, the Kolmogorov picture where all dissipation is happening on three-dimensional, nice, monofractal structures, then you end up, all dq's will be the same as the spatial embedding dimension 3, and the so-called sort of singularity spectrum will just be a delta at alpha equal to 1 and f alpha equal to 3, which guarantees the Hölder exponent 1/3 and the famous Kolmogorov p/3 law, the minus 5/3 law, the 4/5 law, all of that follows. So, if you actually now go back to real turbulence, so this is a snapshot of a dissipation field from, from a huge sort of data set. Then you can sort of play this game again here. You can play it in the full three-dimensional field as we have done, or for visualization, dimensional snapshot. And you can play that game, and then you end up seeing, I mean, we can ignore, but that's the generalized dimension, but then you can see, unlike Kolmogorov, which would have been just a delta function sitting at alpha equal to 1, you see a wide spread of scaling exponents and a wide spread of the associated fractal dimensions on which your dissipation lives. The interesting thing is that, alpha equal to 1 corresponds to h 1/3. What you see is there is enough life at h less than 1/3. H less than 1/3 is what people, really are after. So the caveat, and this is where, essentially our sort of work begins, is that these are global statistics. And so historically, since the 80s, when these ideas came up, starting with Procaccia, Macon, et cetera, and then Charles Menover and Srini sort of pushed it to the critical end, we have been measuring these measures for the full dissipation field. And there's good reason to do it. Now, probably in 2023, we can do slightly better, and that's the story I'm going to tell you. So the question that we were asking is that with such a global measure, does it fail to distinguish hotspots within the flow where things could be more irregular in the sense of Hölder continuous less than 1/3, which you can now start to pick out, right? So how do we go around this problem? In other words, and this is a sort of natural question in my opinion, but that could be an unnatural question to more reasonable people, is the following, that everything else in turbulence seems to vary in space. The dissipation field here is very different from the field there. The velocity here is very different from the velocity there. So if everything is intermittent, why shouldn't the degree of multifractality itself be spatially varying? And if it does, is there a way to actually measure this? So sort of pictorially, and this is the image we had, is can I now construct a field of the Hölder exponent, so move from h to h of x, and Ram is already smiling. Can I sort of move from dq to dq of x, or alpha to alpha of x? And what I would like to see is something of this form, where whatever be my measurement, I see a strong spatial variation. I see regions where h has certain values which are sort of important from the point of turbulent theory. So essentially, we are going to try and connect ideas of cascade with multifractality. Cascade, as we discussed, is an inherently local process, so why should the rest of it not be local as well? And secondly, to sort of detect possible singular behavior, where you might end up finding, if this room is like a wind tunnel, you might end up finding singularities which are spatially localized, and then we sort of start to worry about that. So, this sort of ties in some way with the essential sort of turbulence question, which has to do with the fact, intermittency, anomalous dissipation are things that people sort of, the fact that whatever statistics you measure in turbulence seems to have really fat tails, that's intermittency. And the more interesting problem is that of, anomalous dissipation, which is when you calculate dissipation rates, it seems to go to a non-vanishing finite limit, even when viscosity goes to 0. And this is only possible when you have a Hölder exponent, which is less than 1/3. So essentially, what we are trying to sort of achieve by this sort of prescription, if it's possible, is to tie in these three main issues in turbulence: finite time lob, dissipative anomaly, intermittency, because the answer for this all lies in understanding the roughness of the flow. So we are now trying to go inside the flow and probe if there are regions of the flow which are rough enough to kind of, complete this Venn diagram, as it were. So the question is the turbulent flow uniformly multifractal or not? So as I said, this is sort of ideas that we are developing now, and this sort of question is being addressed or discussed by Datta, who's a postdoc, Sugan, finishing grad student on his way out, and Ritik, who sort of just was working on these ideas for his sort of master's project with me. So how do we probe the local multifractality now that I've built up the story? So what we've done is we've taken these dissipation fields, and the reason this is possible now that these are sort of fields from 8192 cube data, sort of very large, with very large Taylor scale Reynolds number. And what we've done is we've divided this field into tiles, which are now going to be small. So I didn't go through the algebra, but essentially when you calculate the partition function and take the scaling, you go to the r going to 0 limit, right? So we are now sort of tiling our field, and we will essentially treat each of these boxes as our domain. The question is, can we get clean scaling, which is reliable beyond just the three authors of this paper? And so here's sort of, a look at what we've done. So we've sort of calculated the partition function. This is taken from any one of these tiles. I can't tell you which one. And three of these tiles. So there are three bunches of curves. So these are for different values of Q. The scaling looks reasonable, but there's only 4 data points. That's because these tiles are small. That's about the maximum that we can push our line. But we also sort of calculated essentially the Pearson curve to understand the confidence on these measurements. So now comes the main point. Sorry. Yeah, exactly. But there's an interesting thing where what happens when you start overlapping. You have to go and fix the mathematics a little in the weights, the mu measure of each of these configurations. It's very, we can discuss exactly what happened. I'm not going to show that in the talk. So that's the first sort of thing, and I'm nearly done because, it's 1:20. So the first set of data is, let's look at the correlation. So So the classical multifractal calculations going back all these years would have given you one number, D2 for the full, right? But now we are able to have a map of D2 across the field, and what we see is that there is, so this is a zoomed in section, that there seems to be coherent sort of pockets of D2. So D2, 3 would be things which are exactly Kolmogorov. So the local structure there is just a three-dimensional dissipative structure. But lo and this sort of analysis shows us that there are several regions, and that's not a surprise because the global statistics showed this bias, where you end up with dissipative structures which are really fractal and which are, so the whole idea is, are these sort of coherent in some ways? If there is in space, if there's a dissipative structure with a certain fractal dimension, how far apart is it from another structure? We can go ahead and we can actually measure, so this is again a snapshot of some tiles from our plot, from our calculation, where we are able to measure the so-called singularity spectrum, this F alpha curve, and you see even, 6 of these tiles, you see there's a tremendous variation. So for example, one could argue that this curve here is very close to, well, very close to might be an exaggeration, but this certainly looks a more monofractal region, a more Kolmogorov region than, let's say, the curve here, which has a wider tail. So different tiles are showing up sort of different things. So then one had to sort of eventually come up with a measure of multifractality, and the measure that we choose, and this is really ad hoc, is because after all, the singularity spectrum is not a PDF, but what we choose was we are going to define the standard deviation on alpha. We have a bunch of numbers, alpha. I can construct phi as the standard deviation of that alpha, and I'm going to look at this phi field. And this phi varies between 0 and order 1. Actually, you can show, by hand what the upper limit of phi is by assuming a uniform distribution of alpha. The number turns out to be 1.2 or something. But never mind the actual number, but the main point is that with this sort of ad hoc, admittedly ad hoc definition, I can construct a field phi which will vary from 0 to order 1, which will tell me if I'm sitting here in this flow at this point in time, is this region multifractal or not? All right? Sort of, nice way of thinking about it. Again, just to remind you, the classical Kolmogorov picture would be phi 0, alpha equals 3h equal to 1, and f alpha 3. So what does the phi field look like? So here's the sort of, really the semi-final plot. So the phi field shows this tremendous variation. So close to 0, that's the yellow color, is Kolmogorov. So you end up seeing, most of it looks like yellow. So, and then there are these pockets where there are regions which are red to dark red, which are going to be strongly multifractal, right? So, and then, this part I'll probably skip, but then you can sort of, compute the sort of mean phi as a function of the variation in dissipation in each of these tiles and show that it has a nice log behavior. That's again not very surprising because of dissipation statistics in turbulence having a log normal distribution, and one is trying to sort of connect these two ideas as much as we can. So the basic sort of central message right now, and again, as I said, this is really, stuff that Siddhartha, Ritik, and Sugan are pushing, and, they're excited, I'm excited, so I thought I'd speak about this, is the fact, so what is this plot? So this plot is a superposition of the dissipation field, but showing only the extreme events, and the reddish bits is a plot of phi showing only when phi is really, where the field is really multifractal. So phi is not close to 0, we've masked the 0 regions. So what you end up seeing is blue and red. Essentially what this plot is telling you is that wherever phi is low, which is Kolmogorov, you see very little of the dissipation field. So the correlation between extreme events and multifractality is something that we've sort of tried to bring out from this picture, and now we sort of believe in we have taken several liberties both with the English language and the physics of turbulence, but now I think we sort of, this is a definition that I'm sort of beginning to sort of gear the work towards, is that probably we can sort of go back and see that Kolmogorov was probably not entirely wrong, and that essentially turbulence would be the sort of huge Kolmogorovian sea where there are these islands of extreme events and hence multifractality. So with that, I'll just sort of, I'll stress on the word hope more than conclusions, is what we're trying to do is to really map the Hölder field. Hölder less than 1/3 is great news, or not so good news. Hölder less than 1/3 confirms where anomalous dissipative anomaly stems from, and it's a good indicator if there is all-time regularity in solutions of the Navier-Stokes, so that's really what we are after. And for the moment, we are sort of trying to construct 2-point correlators of this field, for what it's worth, to try and see if there is a certain persistence in multifractal behavior. So with that, I'll just end with this because I like this while I pause for questions. So what is this? This is 3 plots. So this is the dissipation field in a cube, and these two are essentially the surrogates of the Hölder exponents, where Hölder is less than 1/3. So what we are trying to zoom in is inside the field and try to see what are the hotspots where the flow might well be singular. So with that, I'll stop, and thank you once again.